Okay, good afternoon. I hope you enjoyed your lunch. We are back to the Pears Foundation webinar. And before we resume with our presentations, Ms. Miri Ben Chaim would like to say a few words, the head of the Division for External Studies. Miri, please.
Thank you, Professor Soranga. I'm glad to open actually the last session of the 2 days webinar, the first webinar of the Pears Foundation. And I would like to thank the Pears Foundation for everything they allowed us to do in this adventure. The Pears Foundation understood that knowledge transfer and education is a force. And I think this is one of the main reasons they invested in this program, and we thank them very much for this. They believed in us and they believed in our way, and this is the result of what has been done in these last few days. By their generosity, they enabled us to build up this whole program, which is very new to the Hebrew University, and this is our first trial, hoping for many more to come. And by expanding activities, they allow us to open up to new programs and to other challenges, and this is why we thank them greatly from the bottom of our heart. Good luck to you all. Please proceed.
So we proceed with our afternoon session, and the first presentation for this session will be by Miriam Silva Ruiz. Miriam is from Mexico. She graduated from the Chapingo Autonomous University in Mexico, and she was later on a research associate at UC Davis in California, and then agronomist with Evogene in Israel, and now a student in our program. Miriam, please.
Hi, good afternoon. My name is Miriam and I'm from Mexico. The person that guided me through this research exercise is Dr. Elbaum, and our research intends to explain that salinity induces changes in tomato fruit texture. First of all, we have to realize that tomato is a cash crop for the state of Israel and all around the world, and therefore the traits that are involved in improving this crop are traits that are going to be related mainly to increasing the yield or to improve the pest resistance or to better drought resistant or to just increase the shelf life. But these traits work really nice for the breeders and the growers since the early 90s because, yeah, indeed, every year the production was increasing and also the value per production was increasing. But in the last couple of years, we can see that the production more or less became stable, and the literature points out that this is mainly due to the fact that the traits that I mentioned before, they reach their final potential. Therefore, the growers, if they cannot increase the yield anymore, so they have to look for traits that can increase the value of their production. Traits that are going to be mainly related to nutritional facts of the crop, to the flavor, to the appearance, overall traits related to tomato fruit quality. So we have to understand the quality is any attribute that will determine the acceptability of the consumer if it rejects or if it doesn't like the product. Attributes of just like how does the fruit look in the shelf in the market, or how does it feel in our hands when we touch it. But the most important of all, how does it feel in our mouth? How do we perceive the flavor? How do we perceive the formation and disintegration of the fruits in our mouth? And the attribute of quality that measures these characteristics is texture. Texture itself has different components like softening or hardiness, and it also has factors that affect texture. The factors that affect texture the most is, for example, quality of irrigation water, and it was observed but not measured by Leonardi in 2004 that if we grow tomatoes under salt stress, the peel will become thicker. And there are also issues regarding tomato fruit texture research. The main issue is that all the studies are focused in the improvement that salinity induces in quality. And there are really few studies that talk about how the salinity induces undesirable changes on quality. And when we're measuring texture, as I said before, we can measure it through objective tests. And the studies that measure texture through objective tests, they don't correlate it with sensory analysis, for example, organoleptic surveys. So the literature says that the best study will be the one that can put the three components together to do objective tests, to do sensory analysis, but even more, the one that does microstructure evaluation of the cells in the fruit. And therefore, the objective of all research is to characterize the overall indicators of fruit quality, but to follow the changes of morphology and structure of the cells in the fruit and see if it affects its fruit texture. And all of it under the hypothesis that salinity induces undesirable changes in fruit and fruit skin, and it affects its quality. We divided our materials and methods in three phases. In the first phase, we didn't destroy our samples. In the second one, we did. And the third phase has to do with the microscopic analysis. The first phase intended to get results related to the whole fruit characteristics and to the peel. So what we did for this was that we set up the experiment in Ramat Negev, Israel, and then we had 5 different cherry tomato cultivars. We grew them on decisimens at 1.5 on the water, 4.0. We had a total of 100 experimental plots, and each plot was properly labeled. When the tomatoes had a markable stage, we harvest them all from the whole plot. The whole plot was harvested in a black bin like this, and then from the bin we took only 5 clusters. We collect them in this sample, and this sample was the one that we actually used for all of our measurements that I'm going to explain. The first measurement that we did was average fruit weight. We took 25 tomatoes. We divided the weight into 25. The second measurement that we did was we took 4 tomatoes and we punched it with this penetrometer. What it tells us, this machine here, is the force required to penetrate the tomato peeled. It brings us the lecture back in newtons. The third thing that we did is that we generated our own scale. We generated 2 scales because even at a markable stage, there was a cultivar that had green stripes, so we had to separate the red cultivars from the striped cultivar. 3 made a nice ripe fruit, and 1 a less ripe fruit. We took 5 tomatoes from our sample, and we graded individually. Then we wanted to see how much does the peeled weight. So what we did is we took this puncher. It had a fixed area of 1 centimeter square. We punched 5 tomatoes. We put the tomato to boil, the peel to boil for around 30 seconds at 98 degrees, and this was to get rid of any extra pericarp that we could be having in our peel. And then we dried it at 60 degrees Celsius for 2 days, and we took the dry peel weight. So we had results that were like related to weight and to color and to force required for peel rupture and dry peel weight. The results were as follows for this first phase. All the statistics were done under the consideration that it was a factorial design with 2 salinity levels, 5 cultivars, and there were 3 effects: the cultivar effect, the salinity effect, and the interaction effect. There were no significant differences in the interaction effect. Therefore, the first part of the graph is indicating the April harvest. The second part of the graph indicates May harvest. And the grouping that you see here with the letters, it's 2K, but it's grouping the different cultivars that are differentiated by different color. In the line part here, it's the salinity effect in each cultivar. So we can say that in terms of the weight, for all the cultivars, their weight when they were grown under salinity, it was reduced. And the cultivar that was the most susceptible as compared to its control 1.5 was cultivar 1335. And the cultivar that was the less susceptible was cultivar DCR 522. But this doesn't mean that were the cultivars that had the higher or less weight. The higher weight was in cultivar 2204 as compared to all the other cultivars, and cultivar DCR 522 had the less weight. In the color, we had some noise here because of the striped cultivar, and I believe this is the reason why we had statistical differences for the salinity, but nevertheless, the cultivar that was the more susceptible in terms of ripeness under salinity was cultivar 2206, and the cultivar that was less susceptible was cultivar 2204. In the penetrometer, the results were totally the opposite. For all the cultivars, the force required for cuticle rupture increased under salt stress conditions. And we can see that the cultivar that was the most susceptible was cultivar 4688, and the cultivar that was the less susceptible was cultivar DCR 522. The cultivar that had the higher resistance to the penetration of its peel was cultivar 2206, and the cultivar that had the less resistance was the same cultivar that was the less susceptible, cultivar DCR 522. This makes sense with the dry peeled weight. In the dry peel weight, all of the weights of the peels increased again under salinity stress, and the cultivar that was the less susceptible was cultivar 1335, and the cultivar that was more susceptible makes sense with also with the penetrometer readings was cultivar 46008. And the cultivar that had the heaviest peeled was the striped cultivar 2206, and the cultivar that had the less dry peel weight was cultivar DCR 522. Then in the second phase, when we started destroying our sample, we wanted to get characteristics that will give us an idea of the juice and the taste. For this, what we did is we did, first of all, percent solids. We blended all of our tomatoes. We weighed them in fresh and then in dry. And then all the rest of the blended material, we filtered it. And then we collected it in an assay tube. We took a liquid of it, and we put it into a refractometer. We did the same for the pH meter. We took the sample from here, we calibrated the pH meter, and we took the reading. The refractometer, it's telling us total soluble solids. For the organoleptic survey, we gathered 31 volunteers for the first harvest, 24 volunteers for the second harvest, and we asked them to grade the tomatoes according to poor, fair, or good for 3 components, for skin thickness, for sweetness, and for general flavor. We ended up with 10 samples per volunteer because we had 5 cultivars, and we had both salinity levels of 1.5 and 4.0 decisiemens. Okay, the results that we acquired were for percent solids, pH, TCC, and the organoleptic surveys were as follows. For all the cultivars, when they are grown under salinity, the percent solids increase. And the cultivar that tends to be more susceptible for the percent solids to increase is cultivar 1335, and the cultivar that is less susceptible is cultivar 2204. But nevertheless, the cultivar that has the highest percent solids, again, is the striped cultivar 2206, and the cultivar that has the less percent solids is cultivar 1335. In the pH and the TCC, we didn't see any effect, not in the interaction, and not on the salinity effect, and not on the cultivar effect, neither for the April harvest and the TCC, and neither for the main harvest on the pH. But we put the results, so you can see that the values were in the average of 4.2 for the pH and 6 for the TCC. For the organoleptic survey, what we saw is from the consumer's point of view, the cultivar for which it matters the most if you grow it in salinity or not salinity is going to be cultivar 1335. And the cultivar that matters the less where you grow it is going to be cultivar DCR 522 in terms of skin thickness. The cultivar that had the lower skin thickness was cultivar 2204 and cultivar 2206. And the cultivar that, even though it didn't matter where you grow it, naturally already had a tougher skin was cultivar DCR 522. In terms of sweetness, we saw that the cultivar that doesn't matter where you grow it is cultivar 1335, and the cultivar that is the more susceptible is cultivar 2204. And in the general flavor, what we saw is that the cultivar that is more susceptible is going to be cultivar 2204, and the cultivar that is going to be less susceptible for its general flavor, it's going to be cultivar 1335. But overall, the cultivar that the consumers prefer the most was cultivar DCR 522, even though it had the higher value of skin thickness. So we took our tomatoes and we wanted to analyze them in the microscope to see the structure of the cells and the composition. And we did two methodologies, light microscopy and Raman microspectroscopy. The first, we wanted to see composition and morphology of the cells. So what we wanted to aim for with light microscopy is that we would take a section of the tomato cube and we were able to have cuticle, and we would have a subepidermical layer here, which is composed by smaller cells and the cells in the pericarp. And I have to make it really clear that the peel is going to be confirmed by two components, by the cuticle and by the subepidermical layers here, and then the pericarp is something else. What we did is that we took a tomato cube around 0.5 centimeters cube, and we put it into a solution of 4% paraformaldehyde in a PVC buffer, PVCS phosphate buffered saline, and we vacuum for 30 minutes so the solution will get into the cells. And then we shake it for an hour, and then we put it for 4 degrees Celsius for 24 hours in the refrigerator. We came the day after, we washed off the PFA. We put a solution of 50% PEG for 22 hours. We wash it off. We put a solution of 100% PEG for 24 hours. And then we put it in the fridge so the PEG will become solid. Once the PEG became solid with our tomato cube inside, it becomes something like this when we take it out of the vessels. So with this instrument here, it's a microtome. We cut sections of 10 micrometers and sections of 30 micrometers. The sections of 10 micrometers, we stain them with methylene blue, all the sections for the same time of 10 minutes. We wash it off and we cover our slices. The sections of 30 micrometers, we took them to Raman microspectroscopy, and we didn't stain them. We just washed the PEG off, and then we closed our slices. So what we did get with light microscopy, we did get our sample with cuticle, with subepidermical layer, and with pericarp, but we also wanted to get montages that will allow us to evaluate differences between cultivar. This is one cultivar, another cultivar, and the third cultivar. The cultivars that were evaluated were 1335, DCR 522, and 46888, 46008. And we wanted to see salinity effect and non-salinity effect. So once we had our montages, we fixed an area, and then with image J, we measured the cuticle area only, meaning the green part here. And the results that we got with light microscopy was as follows. Okay, so methylene blue stains green for lipids. We can see here a cuticle. We have an external cuticle layer. Then we had an internal cuticle layer. We had the subepidermical layer here composed by smaller cells straight underneath the cuticle. We had an epidermical cell here, and we had our pericarp. And lipids is green, meaning the cuticle, and cellulose and stains for blue. Higher concentration of cellulose will stain darker blue. In terms of the area, when we measured with image G, what we saw, there were no differences. The differences were really insignificant as compared to the saline treatments. But let's remember that the peel is not just composed by the green part of the cuticle, it's also composed by the subepidermical layers. And in the subepidermical layers, we saw tremendous differences. For example, if we grow the cultivars under non-salt stress conditions, we will only have 2 layers of subepidermical. Here's one, and here's the second one. And if we go to salinity, we'll have 1, 2, 3, up to 4 layers. And this was repeated in all the cultivars. This was for DCR 522. We can see like there's 1 and 2 subepidermical layers. And here we have 1, 2, 3, maybe 4 subepidermical layers under salt and non-salt stress condition. It also repeated for the other cultivar. You have 1, 2 layers here. When you have here 1, 2, 3 subepidermical layers, and then the pericarp starts. So then we took our samples to Ramen microspectroscopy, and we wanted to see the different composition based on the Raman shift peak. The Ramen microspectroscopy is a technique that what it does is like we not inject, we send a laser energy to our sample, and any component in nature has its molecules that have bonds. When the bonds absorb the energy, they will be excited and they will go to a virtual energy stage, and then they will return. But not all the molecules, not all the energy returns. Only 1% of it won't. And the Raman, what it does, it averages this 1%, and it reflects peaks for different components in nature at a certain Raman shift value. So what the results that we got is that here was our example. We aim our laser. Sorry, I forgot to explain this part here. This was our settings for the Raman. We had it to practice to see what were the best settings. Our Raman region for the components that we were evaluating was 1200. The time of exposure that the laser is open on our sample was 0.2 seconds. It was 10 times the laser was reflected in our samples at only 10% of the total potential energy that the laser can emit. So in the cuticle, we had two major peaks, and then we go to the Raman data database, and we saw that these two peaks are representing cutin. Then we went to the subepidermical layer, and we see that we got pectin here and cellulose here. And then we went to from here we went to the pericarp, and in the pericarp we saw only cellulose, no more pectin. And then we averaged them all without making the differences between 1.0 and 1.5 and 4.0, because we didn't see any differences in intensity here. So we saw differences in composition in between the layers, but not in between the treatments. For our discussion, so we ended up with objective tests, with sensory analysis, and with microstructural analysis. In the objective test, we had smaller fruits grown under, if we grow the cultivars under salinity stress, but with higher percent solids. And we can explain this like as follows. Our differences were around 25%. The literature says that we shouldn't be getting these differences only if we will be working with the Siemens around 8 and we were working with 4. But it also says that the xylem intake, it's around, it reduces it in 25%, and the phloem fluxes into the fruit reduces in 9% daily. The fruit transpiration will increase around 30%, and all of this will bring us less weight of 30% per organ, which is more close to what we had. And then if we are reducing the phloem under salt stress conditions, we are reducing the fruit size. And then if we're reducing the fruit size, we're going to increase the sugar concentration, and we're going to increase also the salt concentrations. Therefore, we're going to end up with smaller fruits, but with higher percent solids, which was what the situation that we had at the end. Then, why did we have higher values of dry peel weight, and why was it tougher to penetrate the peel under salt stress conditions? There are studies done, but only on seeds, on tomato seeds, that under salt stress conditions, the testa of the seeds accumulates cutin and trichome density. And if the cells accumulate cutin, they're going to become bigger, stronger, and heavier, so the force required to penetrate them will also be higher. In the microscopy observations, although we did see the cutin, we saw the pectin, and we saw the cellulose, we think, I'll come back to this, that the main problem was this part here, that we hit 3 different points, and we didn't actually like measure a gradient. And the Raman is capable of doing it. It can measure the whole thing and even give us a map. But because of matter of time, we didn't do this. So therefore, we didn't get any differences in terms of composition. Okay, in the morphology that we saw with light microscopy is that we didn't see any differences in the cuticle area. But again, the peel is not just the cuticle. It's also the subepidermical layer. And in the subepidermical layer, I presented really few pictures before, so I wanted to repeat them here. The top pictures are non-salt stress conditions, and the bottom pictures are salt stress conditions. And you can see that the intensity of the cellulose here, it's thinner than the intensity here. There are less layers all the time under non-salt stress conditions, and we have more layers here with salts. So we do believe that there is a differences in not just in cellulose concentration underneath the cuticle, but the toughness is based here. Okay, so just to put it all together, we decided to start with which ones were the cultivars that the consumers like the more. Okay, so they like more 1335 and DCR 522. The problem is that these cultivars are the ones that are most effective or more susceptible for the peel thickness, and even DCR, it's the thicker, the one that has a thicker peel from the consumer's point of view, and this was reflected in the light microscopy because they have up to 4 and to 5 subepidermical layers when they are grown under salt stress conditions. And we will suggest that these two cultivars will be the ones that will be further studied to improve their salinity susceptibility. Our conclusion will be that all the changes that induced in tomato fruit texture under salt stress were originating from thickening the peel, but not in the composition. And as conclusion, we will accept our hypothesis that high salinity conditions do induce undesirable changes in fruit and in fruit skin texture, affecting its quality. And thank you, and thank you all the persons from my lab because they were really patient with me. Yeah, I was willing to teach. Thank you.
Hi, it was a beautiful presentation. Just because I'm thinking about now Zerai's presentation, because he showed there that there are some genes that can have like can have a good can have a good trait, and then the same can have a bad trait. So your conclusion like was consistent with all your results, like all the ones that were exposed to the salinity. They had
undesirable changes.
Undesirable. Okay.
Mm-hmm.
And the thing you concluded that the salinity stress,
Yes.
it causes undesirable changes.
Mm-hmm.
Will the character be same in resistant and susceptible varieties, or what?
For
Or we
all,
will
for
get
all
some
the, well, we
difference?
saw that for all the varieties. I just point out the ones that were more susceptible and less susceptible, but for all the varieties, we had undesirable changes in all of them, and all the effects were
Or
significant.
it means the trend will be same, even it is susceptible or resistant, it doesn't matter.
Well, we don't have a background that we can say, okay, we think these cultivars are resistant. We just wanted to evaluate them. We didn't know if they were actually resistant or not resistant.
Thank you.
Mm-hmm.
I would like to know if you observe the yield of the tomatoes in the greenhouse.
The what? Excuse
The
me?
yield of the tomatoes in the greenhouse.
The yield?
The yield.
No, we didn't observe the yield. In Ramat Negev, they do have records of the whole yield plot in the computer, like I showed you in the beginning, right in the beginning. But we just took 5 clusters per sample. They have records of the whole thing. Oh, it's too bad. Here, you see, we had the whole plot, like let's say from here to here, and we collected all the markable clusters, and we put it into these beans, and we did record the yield of the plot, but we didn't, for our studies, we didn't use the whole yield plot. We only used the average weight of 25 tomatoes from 5 clusters of the plot.
Okay, my question is, like, I wanted to know how the yield it looks like in the high salinity conditions. Yeah, that's what I wanted to find out. But since you said you didn't do it,
well, the literature says that if you're working with 8 decimins, you're going to start to have 30% decrease in yield.
yeah. Okay. Thanks.
I have heard that the tomato under salinity stress has more sweeter taste than the tomato under normal water condition. Do you know the reason why is it? And if you did you notice the difference in TSS content between the?
Yeah, with the organoleptic test, we saw it was sweeter, and also with the percent solids, we saw it was sweeter. The percent solids in the total TCC, total soluble solids, it's an indicator. It's actually an indicator of sugars. So it increases because you have less water in the fruit. So you have more concentration of the sugar, and you have more concentration also of the whole percent solids.
One question, if I get right or not, if we grow tomato on the normal irrigation and under the saline, then the peel thickness will be higher in the saline irrigation.
Mm-hmm.
Can we generalize it for the other tomato varieties also? Can we generalize this?
I didn't find any studies that were related to the peeled for the markable tomato, for the big tomato, but it's only seen in seeds that it does influence in the seed, but not on the peel, not exactly on the peel. Because all the studies are based on the good things that salinity does for quality, but not on the desirable changes.
Okay.
Other questions? Yes, here.
Miriam, do you look on the locule? The structure of the locule might be? Some people prefer in the texture to look on the structure of the locules and...
Sorry, I don't know. The structure of what?
Locules.
QTLs, you mean?
Locules is the internal part of the...
of the cell, you mean?
Yeah.
No, we just stain for the cell wall. With the chemical that we use, methionine blue, it only stains for cell wall composition, in this case cellulose, and for the lipid composition, for the cuticle composition that was lipids, we didn't stain for.
So this thick skin, you consider it as bad, like a bad trait, rather than... Because some people may appreciate to have a thick skin which can, for example, for shelf life, even when they are growing in high water content, they can be cracked with a short period of time. So it will have.
That might be good, like you said, probably to have a thicker cuticle for processed tomatoes, for big tomatoes, but for cherry tomatoes, that's not a trait that you would like to have. And you can see it in the Organoleptic Survey results. The consumers don't like to have a thicker peel. Yeah.
You use 4 decimine per meter as stress, right?
Yeah,
What's
on
your
water.
base? I mean, what was your base to use that one?
That's what the research. That's what the research had on said, 1.5 and 4.0. Okay. And I guess that through the time they were thinking that because this value is for the water, that with 4.0 you will be accumulating the salts in the soil afterwards.
Okay, I mean this one the concentration of salinity in the irrigation water there in the negative, or
that's the concentration of the salt they were irrigating with, 4.0.
Normally the irrigation water had this one.
No, I don't know the value of
I mean,
the normal irrigation water in the station. I don't know.
Okay, maybe had you been using different rates of salinity concentration, I mean, maybe.
Yeah, it can be possible to. It would be good to evaluate different salinity levels rather than just 1.5 and 4.0.
Until the microphone moves to the other corner of the room, let me ask you something, Miriam. As I understand, with the Raman, you just identified qualitatively what is the major compound in each layer, right?
Yes, but we could have also done it to quantify.
So it can be quantified.
Yeah.
However, in your conclusion, you said that the composition did not change, only the number of layers changed?
No, I said that, yeah, the composition
Of
in the layers, on the layers from 1.0 and
Right.
4.5 didn't change in each specific layer, only in between layers we had, for example, cutin that we didn't have in the pericarp, and we had pectin that we didn't have in the cuticle.
Okay,
I didn't
but
understand your
between the
question.
1 and the 1.5 and the 4, between the different salinity levels, you say that there was no, let's say, qualitative difference in the major compound, but yet was there a difference in the, let's say, amount of pectin deposited or any other compound there?
We saw there were no differences between 1.5 and 4.0, let's say, for cellulose. And then there were no differences in, for the cuticle in 1.5 and 4.0, there were no differences for the cutin concentration. You understand? And then for the subepidermical layer, for 1.5 and 4.0, we didn't see any differences in concentration for cellulose and for pectin. And then for pericarp, we didn't see any difference in concentration in cellulose for 1.5 and 4.0.
What do you mean by concentration?
I don't want to call it concentration because it's not an exact measure of concentration, but it's a measure of intensity.
All right, but you did show some difference in intensity, at least in the cuticle, isn't it?
No, it's different components for each one of them. Let me put. You see this one here? The blue one represents the cuticle, and it only has cutin. And then we have the second one that it's the subepidermical layer, the red one, and it has pectin and it has cellulose. And then the pericarp only has cellulose. What we saw, we did have the spectrum. We did have different spectrums, for example, for cutin, for cuticle, for cutin, for 1.5, and we had a different spectrum for the same component in the cuticle, but we didn't see any difference in intensity, for example, here. We have two, maybe you're confused because we see two peaks here, but they're both representing bonds in the molecule of
yeah,
cutin.
I understand that. But still, what are the differences between the treatments, I mean, in this respect? You say that you saw the same peaks, however, peak represent, the peak represents the quantity or only the quality? Namely, identifies what compound is there.
If you decide that the peaks are similar, like let's say, I didn't even graph it. Let's say, for example, the red and the green. Let's say that the red will be 1.5 and that the green will be 4.0. And then you have this difference here, this delta here, in intensity. If you decide that the peak length is the same, you are sure that that peak is representing you cellulose. Therefore, you can compare the delta in terms of intensity for cellulose.
Okay,
so we can say, okay,
so what did you find out in this respect in comparison between the 1 and the 1.5 and the 4?
We just saw that yesterday.
Oh, okay.
That's what we were discussing yesterday. That in the 1.5, we have a lot of fluorescence in the sample, so we're not sure that we're measuring the same exact bonds for cellulose, so that's why we didn't want to make the assumption that there was differences between 1.5 and 4.0.
Okay, so you still don't have, you're not sure about it.
Yeah, I don't want to make any assumption because we're not sure, but we will see.
Okay?
Yes, my question is on the salinity level, how the various salinity level you used affected the nutritional level, let's say vitamin C. That is, if you were looking at those components, the vitamin C, did you also look at how the various salinity level affected the nutritional components of the fruits?
We didn't measure any nutritional facts like level of antioxidants or stuff like that, but I will assume that it will increase the concentration of any, for example, vitamin C or any other component. It will increase the concentration because it has less water on the fruit, I'm believing. That's it.
We have a few minutes for a last question, if there is any. Okay, if not, we will thank Miriam very much. For the sake of those that may be watching us on the web, we will wait 3 to 4 minutes until we will start with the next presentation, okay? רבקה? 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 קיבלת טופס מ... סתם היה פה שהשאירו לי את זה עם התעודות. לא נורא, לא עת יוקרתי. כמו אתמול. מרים? All right, so we shall move on to the next presentation that will be presented by Kwesi Bordoh from Ghana. Kwesi has completed his first degree, BSc in Agricultural Technology at the University for Development Studies in Ghana. And he is currently an MSc student in our international program here at the Hebrew University. Where is that? Here it is. And Kwesi will present us his seminar on the influence of hot water rinsing and brushing on tomatoes' internal and external quality. Please, Kwesi.
Thank you very much. My name is Kwesi Bordoh, as Prof. Saranga introduced. And the title of my presentation is The Influence of Hot Water Rinsing and Brushing on Tomatoes' Internal and External Quality. This experiment was done at the Department of Post-Harvest Science in the Agricultural Research Organization and the Volcanic Center under the supervision of Professor Fallik. Unfortunately, he's not here, so he has sent someone to sit in for him, the person of Jacob. And the order of presentation is as follows. I'm going to look at the introduction, the objectives, materials and methods, results and discussion, and the conclusion. Now, as part of the introduction, most harvested commodities need to be free of disease, insects, synthetic chemicals, and cleaned before they are packaged and exported. Now, the susceptibility of fresh harvested produce to post-harvest diseases increases during prolonged storage, and this disease may be as a result of physiological and pathological deterioration. And as it stands now, there is no post-harvest fungicide that have been registered for the control of decay-causing agents in tomatoes. Now, even though there are other non-chemical technologies which are also used to control decay-causing agents and also prolong the shelf life of tomatoes, some technologies, like I said earlier, have been developed, and some of which include irradiation, the use of materials that are generally regarded as safe, GRAS for short. We have hyperbaric treatment or modified atmosphere packaging. Now, all these treatments are non-chemical, and they have also proven to be a very good method or technology to control decay in tomatoes. However, heat treatment happens to be one of the promising means for post-harvest control of decay, as has been discussed by Coy and Lurie in 1989 and then 1998. Sorry. Now, heat treatment, like I said earlier on, may be applied to not only to fruit but also to vegetables, using hot water dip, vapor heat, hot dry air, and then hot water rinsing and brushing, of which my research was all about. Now, some of the benefits of using this technology is that it's very easy to use, and the treatment time of washing the fruit is very short. And aside that also there's reliable monitoring of fruit and the water temperature, as well as very effective and efficient in killing of skin-borne decay-causing agents, which are mostly found on the skin or the peel of the fruit. Now, Lurie et al. 1998 said the optimal temperature to treat fruit before storage at 12, and the recommended storage temperature of tomatoes is 12, can maintain the quality parameters by reducing decay incidence and chilling injury. Now, to support this claim, research has been done over the years by Fallik et al. 93, 2001, and 2002. And in his research, tomatoes were exposed to a temperature of 38 degrees Celsius for 3 days. And in another experiment also, this technology was also used where the tomatoes were washed at a temperature of 52 for 15 seconds prior to storage. But after storage, they noticed that there was decay development was inhibited without affecting the fruit quality and other parameters. And apart from alleviating certain physiological disorders, which I've mentioned earlier on, like decay and chilling injury, the heat treatment also maintains and improves the antioxidant defenses. I must also say that the tomato have a lot of antioxidants in it, like vitamin C, carotenoids, to mention but a few. But paramount among them is the vitamin C. And in an experiment which was done by Coy et al. 2006, when heat treatment was used for mushroom, raw shiitake mushroom, Letinus edulus, and at that 100 degrees and 120 for 15 and 30 minutes using autoclave before storage, they realized or they observed that the antioxidant activity was maintained and improved. So in this experiment, we also wanted to find out that at what temperature, that if we wash the fruit, and at what maturity stage, that if we harvest the fruit before storing, and at which storage temperature can maintain these qualities that we are talking of, as well as inhibiting decay and chilling injury. So the objective of this study was to determine the influence of hot water rinsing and brushing on tomato Solanum lycopersicum, which is also called Lycopersicum esculentum male, the external and the internal parameters of vitamin C and the total antioxidant activity, which is what we are most interested in, because the total antioxidant activity, even though has been done in tomatoes, but not with this technology. So this is the first time that this technology has been used to determine the total antioxidant activity in tomatoes after prolonged storage and marketing simulation. Now, to achieve this objective, we have this methodology. Now, the tomato fruit was harvested at 2 stages, as you can see, matured green and pink. So whenever you see pink, it's just an abbreviation of my short name, PK, without effect. And the fruit were harvested every 3 weeks for 3 to 4 months. And this experiment was repeated 3 times from commercial non-heated plastic house in the central region of Israel. Now, what we were looking at is that we wanted to look at how the heat treatment, like I said in my introduction, is able to influence, we categorize under 3, the external, the internal qualities, and the nutritional level. For the external, we're looking at the weight loss, firmness, and color, as well as decay incidence. And then the internal quality, we're looking at the titratable acidity, that is TA for short, and then the TSS, which is the total soluble solids. And then the nutritional compound, mainly vitamin C and antioxidant activity along the growing season. Now, before the heat treatment, the fruit were sorted out according to uniform color and size for the pink. And then for the matured green, it's much obvious because the green is green, you can easily see. So the green was sorted out according to its size. And then the fruit calyx were all removed. Now, the temperature that we use for our treatment was we wash the fruit at 51 and at 55 for 15 seconds, whilst the 22 served as our control. 22 is the temperature for mostly for tap water. So we wanted to see if we use tap water in relation to the heat treatment, what would be the effect. Then after the heat treatment, the fruit were then stored at 2 separate temperatures. That is for both pink and matured green, at 5 degrees centigrade and at 12 degrees centigrade for 3 weeks, plus 3 days of shelf life. And the emphasis of this was a simulation of seed transport to Europe and marketing. So in total, we had 12 treatments, and each treatment consisted of 25 fruits. Now, this is just a schematic diagram of the machine. And as you can see, the first column you see here is the conveyor. The fruits are kept here. They are conveyed into the washing chamber. The first chamber is for the control, and the third chamber is for the treatment, the heat treatment that we want to look at. Now, when this one is in operation, this one is shut down so that it doesn't have effects on the treatment. And in the heat treatment section, you can see at the bottom here, we have the hot water container. So this pump recycles the hot water, and the fruits are washed as they move along this conveyor. Now, these black round things you see are the brushes. They are very soft, so as the fruits move along, they are brushed gently, and they don't have any effects on the fruit. Then they are then conveyed to the dryer, and they dried approximately at 22 degrees Celsius for some few minutes, seconds, and then they are separated or sorted out according to the storage temperature that we want. So this picture here you see, it is a clear picture of the machine. As you can see, that is me doing my own thing. That is the washing chamber. This one is for the control, and this one is for the heat treatment. And as you can see, the fruits are moving gently, and the water drops on it. It rinses, it is brushing it, and that's how the name of the machine is. It rinses, and it is what? It is brushing. So that is the name of the idea behind this technology. And then this is the dryer. Okay, so from here it goes to the dryer, and then it dries it. Now, after the heat treatment, we, like I said earlier, have to take all the parameters. Now, the parameters has to be taken in such a way that we had to destroy the fruit at a point in time. So we had the destructive and then the non-destructive. And the non-destructive basically has to do with the external qualities. So we look at the weight loss, like I said earlier, the firmness, the color, and then the decay. And for weight loss, firmness, color, we used 9 fruits representing the 9 replications. And then for the decay, we took into consideration all the 25 fruits. Now, the weight loss was measured using the Sartorius electronic scale, and that is it over here. and it was calculated as the percentage weight loss from the initial weight. And then the firmness was measured using the durometer, and that's the durometer. And the durometer has no physical unit. The values were arbitral numbers. So the higher the value, the higher the firmness, and the smaller the value, the lower the firmness of the fruit. And then the color was measured using the Minolta chromometer. Higher values means higher inhibition of color, and lower values means the inhibition is very small. We will look at this when I discuss the results better. And then the decay, we considered fruit as decayed when we saw a mycelium, that is after we've taken them from storage. And for the decay, the replication was based on the number of experiments. But for each treatment, we calculate the percentage decay out of the 25 fruits. Okay, so we have the internal qualities. The internal qualities, we have 9 replicates from the external. And then for TSS, we had 9 replications. The TA also, we have 9 replications. The TSS was measured using the digital refractometer, as you can see. And then the TA was measured using the automatic titrometer. And the TA was expressed as the percentage of citric acid. Now, for the nutritional compound, that is for vitamin C and the antioxidant activity, we had 36 treatments. Now, 36 treatment was used for the vitamin C. So the 36 treatments represented the 36 replicate. And the vitamin C in this case, which is an antioxidant in tomatoes, was expressed as the ascorbic acid content in the fruit using the ascorbic acid kit test from HANA instrument. And then the antioxidant activity was determined using DPPH solution. Actually, it is a freshly prepared diluted DPPH solution. And with this method, we had 180 replications. And each replications were put in this is what we call the cavity. So they were put in this cavity, 180 of them, and prepared for the spectrometer, the Ultra 2001 spectrophotometer, sorry. And based on that, we have a data sheet which was generated, and we use this formula to calculate the percentage of inhibition to determine the antioxidant activity, as was described by Abalaka et al. 2010. Now, my analysis was performed according to factorial design using the JAMP 8, and significance was done at 0.05% significance, and I used mostly Microsoft Excel to draw my graphs. But the data, the tables presented in this presentation was presented using the F values. I use the F values to present. All right. So now let's look at the results. Now the first result is the decay incidence. And as we can see in the decay incidence, the heat treatment at 51 and at 55 inhibited chilling injury at 5, because that's why we normally find chilling injury. And at 12, we noticed that there wasn't any decay in both pink and matured green. But when we come to 12, you notice that the pink fruit decayed, some of them decayed. And the reason we can see from this picture here that at 5, this is the pink and this is the matured green fruit. And at 5, this is a control. There was decay in the pink, and then decay also started developing in the matured green. Then also, if we look at 12, a similar situation happened. This is the pink, and then this is the matured green. And then at 55, we also had a similar situation. And this decay was actually due to the heat damage because this temperature was very high. So we believe that because of the high temperature, it might have resulted into, the decay at this temperature. So in general, we can say that these two heat treatments at 51 and at 55 significantly inhibited decay incidence. But it was more pronounced, as you can see, in 51 than in 55 for both maturity stage of the fruit. And the reason why you will find the inhibition for the decay was that in a research which was done in grapefruits, they noticed that the pathogenesis-related protein which are found on the skin of the fruit. The thermal or the heat treatment induced these proteins, so they were able to serve as a defense for the fruit to fight these pathogens. All right. Now the next slide is the weight loss, and for the weight loss, we never had any interaction between the heat treatment, the maturity stage, and the storage temperature, but we noticed that there was interaction between the maturity stage and the temperature. And as you can see, at 5, when the fruit was stored at 5, you notice that the matured green lost weight, even though there was no significant. And then at 12, we'll notice that, except in the control, but at 12, we notice that the matured green lost weight more than the pink, whereas in the other one is the other way around. So we can see from this data that these two heat treatment, even though there wasn't any significant difference between the heat treatment on the maturity stage and after storage, we believe that this heat treatment were able to reduce the weight loss, as you can see at 5, and then at 12 you can see, but in the control at 5 there was too much weight loss over here. And then for the firmness, we didn't have any interaction between the heat treatment, the storage temperature, and the maturity stage. Sorry, between the heat treatment and the storage temperature, but there was significant effect of the maturity stage. And as you can see, at 5, the storage temperature had a significant effect. And at 5, most of the fruit, you can see that the fruit were much firmer at 5, both in pink and then in the matured green. And then the the matured green was much firmer than the pink fruit. That is after storage in all the temperatures. And if we look carefully, when we did the student t-test, we noticed, even though there's no significant difference of the heat treatment, we noticed that these two treatments somehow was able to maintain the firmness of the fruit, that is at 51 and then at 55. But the recommended storage temperature, like I presented in my introduction, is 12. And as you can see in 12, the pink you can see here was not the same, but in 51 and 55, it was much higher. And we think that this heat treatment was able to maintain the firmness. And then for the color, we also noticed that for the color, the heat treatment, the maturity stage, and the storage temperature had significant effect on the color. There wasn't any interaction. And if you look at the chart here, you notice that at 5, there was significant inhibition of color, especially in the matured green. Whereas for the pink, they ripened normally. And if you look at 12, both pink and then the matured green at this storage temperature, they ripened normally. But the inhibition of color was more pronounced in the matured green, especially at this temperature at 5 degrees Celsius. So we can say that these two heat treatments, that is 51 and 55, significantly inhibited the color, and then it was much pronounced at 55 than at 51 in the color. Now, when we look at the TSS, the total soluble solid, we didn't also have any three-way interactions, but we noticed that the maturity stage of fruit, the pink had a high TSS. The pink had a very high TSS, as you can see, after storage at 512. And the interaction was that at 12, at 5 degrees, you can see that even with this heat treatment, the TSS was very high in pink as well as in this heat treatment. And then at 12 also, the TSS was a little bit low under each of the treatment. Now, if we come to the control, we will realize that the TSS was very, very high. And the reason being that at this stage, most of the fruit ripened. And the TSS mostly increases according to the ripening process, as been shown by the color development. And if we look at the vitamin C also, the vitamin C, the heat treatment didn't have any significant effect on the vitamin C. The maturity stage had significant effect on the vitamin C. By the storage temperature, we didn't see any significant effect. So you can see in the graph that this heat treatment improved the vitamin C at 5. And it was also, vitamin C was also improved at 5 for the control. So we can see here that the pink fruits were having a higher vitamin C as compared to the matured grain. Now for the antioxidant activity, we also noticed that the heat treatment, the maturity stage of the fruit, and the storage temperature also had effect on the antioxidant activity. But most importantly, we noticed that most of the heat treated fruit, even though there wasn't any significant difference, but most of the heat treated fruit had a higher antioxidant activity, especially at this storage temperature, which of course was not different from in the control at 12. But in the decay, we noticed that there was decay in the control at 12, and there was some decay also at 5. So if we are considering which type of treatment you want to use, I mean, which treatment is better or something like this, then we will consider these two heat treatments, since here there wasn't any form of decay or any chilling injury. So in the antioxidant activity, this heat treatment was able to maintain or improve the antioxidant activity. All right, so this is just the table of what I have presented in most of the graphs. And in the weight loss, we didn't see any significant effect of the heat treatment. We didn't see any significant effect of the maturity stage. We didn't see any significant effect of the storage temperature, but there was interaction between the maturity stage and the temperature. And when we come to the firmness, the heat treatment didn't have any significant effect, but the maturity stage and the storage temperature had significant effect on the firmness. And when we come to the color, these three main effects had significant effect on the color, and we saw some interaction as I showed in the graphs, that the maturity stage and the temperature, there was a significant interaction. And for the decay, we also saw a significant effect of the heat treatment on decay, and we also saw significant effect of the maturity stage on the decay. And if we look at the TSS, the TA, vitamin C, and then the antioxidant activity also, is the heat treatment had effect. The maturity stage, we also had a significant effect, and we also had an interaction, a significant interaction between the heat treatment and the storage temperature. But we didn't find any significant effect of the heat treatment, the maturity stage on TA, and there wasn't any interaction for the TA. And when we come to the vitamin C also, the heat treatment didn't have any significant effect, but the maturity stage had significant effect on vitamin C. Whereas in the antioxidant activity, heat, maturity stage, and the storage temperature had effect, and there wasn't any interaction whatsoever. So in my conclusion, a combined and optimal hot water rinsing and brushing at this temperature of tomato, especially at the pink stage, and after storage plus 3 days of shelf life, at this temperature maintain the keeping qualities, that is the TSS, vitamin C, and then the antioxidant activity. Now, in literature, we noticed that the TSS, the color, had somewhat a correlation in the sense that as the fruit ripened, the total soluble solid also increases. But if the fruit doesn't ripen so much, it also have some effect also on the total soluble solid. And the vitamin C and the antioxidant activity, we noticed some kind of correlation, even though I didn't put it here, but it wasn't something that was so much interested in about the correlation. But we noticed that as the vitamin C increased, because the vitamin C in itself is an antioxidant. So when the vitamin C was increased, especially the heat treatment at this, we also noticed that the antioxidant activity also increased, and especially at this temperature or that temperature. We also noticed this heat treatment maintained the firmness of the fruit, even though the matured green was much firmer after storage at this. And this heat treatment also maintained the ripening process of the fruit as well as for the matured green. And most of the fruit, both the pink and the matured green, they ripen normally at this storage temperature, as was shown by the color development in the graphs, the graphs that I showed. Also, we believe that this heat treatment significantly inhibited decay incidence after storage at 12, and then was able to reduce chilling injury. Now, the reduction in chilling injury is that with chilling injury, research has shown that in the peels of the fruit, there is a protein, that is the heat shock protein, and the thermal stress induces this protein, and that makes it become sort of able to resist or be able to become resistant to chilling injury, especially at very low temperatures. So we think that this technology should also be explored on a broader range of fresh harvested commodities for minimally processed products, since it reduces the risk of health problems due to the fact that the treated fruits are devoid of chemicals. Because as you can see in this treatment, we didn't use any chemicals. We only used the water to wash the fruit. So we think that it should be explored not only in tomatoes but in other commodities. And then finally, we also think that the enhancement of the fruit tolerance to low temperature by reducing chilling injury or by enhancing fruit resistance to decay-causing agents could allow prolonged storage at temperatures which are lower than currently used. And this will increase the possibility of some commodities to be exported by less sea transport rather than by air transport. Thank you.
We're ready to take questions.
Thank you for your presentation. That was a nice one. My question is, I want to know the importance of the removal of the colors, because somewhere in the materials and methods it was mentioned that the colors of the fruit was removed before the treatment.
Okay.
And I've read somewhere or I understand that the colors prolong the shelf life of the fruit. But in this treatment, it was removed. I want to know if there's a special reason for that.
Okay. I'll explain it using this machine. The colors was removed because when the fruits are being rolled on the brushes over here, we don't want a situation whereby it will get stuck in the brushes. Or better still, because it is sharp, the color is pointed. So if they roll on the brushes, there's a tendency that the colors can even destroy the skin of the other fruits. So to avoid that, that is why we remove the fruit calyxes for this treatment.
Okay. Is in your first graph of your results, it shows that at 55 Celsius, that temperature was high enough to give injury for the pink, but not to the mature green.
Yes.
And do you have an idea why is that?
Yeah. Well, I think that at this temperature, the pink, of course, was susceptible to the heat damage that caused the decay. And the matured green, of course, we didn't see any decay. And literature has shown that in the skin of the fruit or the peel, there's this pathogenesis-related protein like chitinase, which when induced by thermal stress, okay, can help to prevent any pathogen attack. So we think that this was more expressed, this gene which was responsible for producing this protein was more expressed in the matured green than in the pink. And so the heat treatment would have caused more expression of that gene in the peel to be able to induce the decay in the matured green than in the pink. Yes.
PK, do you have any explanation, or can you speculate on how this hot water treatment enhances chilling resistance or tolerance in the fruit?
Okay. For chilling injury, some researches have been done previously, and at 51 and at 52, it's able to inhibit chilling injury, but below when you watch the fruit at 22, we notice here that there was still some decay, which is due to the injury. And the reason why we didn't have any injury at 5, chilling injury at 5, is that there's a protein, that's a heat shock protein in the fruit, which when expressed as a result of the thermal treatment is able to inhibit the injury, especially at this temperature. So we believe that the thermal condition or the heat treatment probably might have induced this gene, which is responsible for inhibiting chilling injury, to be expressed more at heat-treated fruit, and so we were able to inhibit the chilling injury.
Thank you. Why is it important to include 51 and 55? I don't know. I don't understand why.
Okay.
Maybe either of these two temperatures may be enough to test this experiment. You have a long gap between, maybe you consider 22 as a control and you have 51 and 55. I think in most of your data, there was more or less, there was no significant difference between the two, right?
Yes.
So I don't know why you included 55 and 51.
Okay. With previous researches that has been done, and from literature, when fruit were washed above 55, we saw decay. But in some fruit, some varieties of tomatoes, there was inhibition of injury, and in some variety, there wasn't any inhibition of injury. And we chose 55 and 51 as our heat treatment because 52, 53 has been done. So we also wanted to see that at this temperature, is it also possible to inhibit the decay incidence as well as inhibiting chilling injury? So that is why we chose. So the idea, we washed this fruit at 51 and at 55. That's where we washed it. But in my materials and methods, I mentioned that Fallik et al. Also did a similar experiment, but it wasn't at 51. It was at 52. So 51 plus or minus 2 will not have any will be able to inhibit decay and chilling injury. But something above 55 or 55, of course, can inhibit chilling injury, but decay, it can cause decay due to heat damage. And the reason why we use 22 is that, of course, most of us, when we go to the supermarket to buy fruits or the tomatoes, we wash them with tap water. And we assume that approximately the tap water is around 22 degrees Celsius. So by using this storage temperature, you want to see if you wash your fruit with tap water and then you put it in your fridge for some time, what is going to happen after a very long storage. So the rationale behind the 22 is we want to purge it at using tap water if you want to store your fruit.
Yeah, that's fine. 22 is fine, but 51 and 55 is not convincing to use as a separate treatment.
But there is convincing because if you look at the, of course, in the other parameters, we noticed that there were no significant differences and all that. But in the decay, and like I've shown in the, excuse me, here, of course, there wasn't any significant difference in weight loss. There wasn't the heat treatment. But if we look at the color, there was, when we did the student t-test, we noticed that there was significant difference between the heat treatment, between the heat treatment on color. And the inhibition was much higher at 55 than at 51. And one thing we should know is that color also plays a very important role in the ripening, because as fruits ripen, they change color. So the color is an indication to tell us whether the fruit is ripening and whether it's deteriorating very fast. So if we're able to inhibit color at a certain temperature, then it means that we can prolong the shelf life of the fruits. And the heat treatment was able to do that for us, especially though it matured green than in the pink.
Okay, thank you.
This one?
I don't know if I'm understanding right the graph, but you're saying that for 22 degrees after you store them at 5 and at 12, the fruits lost more weight at 5?
Yes.
Why would the fruit, and I think it is more or less in all of them, why would they lose more weight under lower temperatures? It's supposed to be that they wouldn't lose weight at lower temperatures.
Okay, let me start with the heat treatment at 51 and at 55. You know, at 55, when you wash the fruit at this temperature, you see if we didn't do that, but if we are taking a microscopic image of the peel of the fruit, you see some layer of wax around the peel. So this wax at this temperature was able to seal the visible openings on the peel. So that would have accounted for some reduction in this heat treatment. But of course here, there wasn't any crystallization of the wax around the peel. Other factors could also contribute to weight loss, not only the wax, like the frequent opening of because we did it in a storage room where people were also keeping their fruit and all that. So opening and closing of the storage room can also change the atmospheric condition. I mean, temperature, relative humidity and all that. So that could have also been a reason. But here, we're looking at how this heat treatment was able to do the trick, and we noticed that there's recrystallization of some wax around the peel, which sealed the visible openings, so we're able to reduce the firmness. And it was the same thing in the weight loss and in the firmness.
Other questions, guys? Okay, if so, let us thank PK for his presentation. And again, as yesterday, due to the mistake in the timetable, we shall have a longer coffee break, and then we shall convene back for the last presentation of this webinar by our by our guest lecturer, Pears alumni guest lecturer. Okay, so we shall convene at 3:35.